When I originally did this question, the first thing I did was draw the radius of the small circle in and actually work out what that was, because pi r squared is going to equal 1. But it turns out that you end up with fractions involving pi. It's a little bit messy, so I'm going to go through it how the solutions did it, and it is quite nice. And what they do actually is first of all introduce the smallest radius, and that is the radius of the semicircle. So we'll call that r, which means the diameter is going to be 2r. If I now introduce the radius of the circle by drawing these lines in, then this must be a right angle because there's symmetry going on in the question. There must be 4 right angles in fact. And so because this is 2r, this must be root 2r. In the previous question, I actually talked about that result, about how you can just times, if you ever have an equilateral triangle, sorry, not an equilateral, isosceles triangle, say x and x here, then this will necessarily be root 2x. So I'm just doing the result in reverse. I'm dividing my hypotenuse by root 2 to get back to the side lengths. I'll just go ahead and quickly prove it. So x squared plus x squared square rooted is going to equal the square root of 2x squared, which we can then separate into root 2x. So 2r divided by root 2 becomes root 2r. Right, now I can actually put another line in and I create another isosceles triangle, 45 degrees here and here, which means that this is also, because I know that this is 45 degrees, I should have sort of pointed that out. How do I know it? Because I know that it's isosceles and I know that that one's 90. So if I take my 45-degree triangle and split it into two, I'm still going to have 45 degrees. And actually what that means straight away without doing any further calculation is that this is going to equal r. So what we see is that the ratio of the radii for the small to the large circles is going to be root 2 to 2 because the small radius is root 2r and the large radius is 2r. And if we square that, then the area ratio, this is the radius ratios, the area ratio becomes 2 to 4, which is the same as 1 to 2. So actually I've not had to use that one up until this point, but now we just need to times the area by 2, giving us the area of the outer circle as 2. Nice. I will just go through my original way of doing it because you might prefer it. You might think like, and I think I might be thinking the same. I wouldn't have thought to do that. So I kind of jumped in and said, okay, right, I've got pi r squared equals 1. And that means r squared is 1 over pi. So r is the square root of 1 over pi. Or maybe I just write it as 1 over the 1 over the square root of pi. Same thing. Okay, and then, so I've got that, yeah, that is this here. Right, now I introduce the radius of the semicircle. So these two here. And going across is going to be 2 lots of the radius, and I can connect this up as 1 over root pi as well. Okay, now that is useful because now I've got my triangle, my 45-degree isosceles triangle, so I can work out the diameter. In fact, that's going to be, I remember, like I said before, we just times by root 2, so I'm going to get root 2 over root pi. This is for the semicircle. And that means the radius I need to divide through by 2, which becomes 1 over root 2 pi. Because when I divide through by 2, it's the same as dividing through by root 2 twice. So if I divide through by root 2 once, I get 1 over root pi again. Divide again, I get 1 over root 2 pi. Okay, so where does that leave us? Well, actually, it leaves us with 1 over root 2 pi here, and then also here. So I'm just going to write it once because otherwise it's going to get a bit messy. If I draw a line going down the middle, actually I see again I've got this isosceles triangle, so this must also be 1 over root 2 pi, which means the radius of the large circle is going to be these two added together. It's going to be 2 over root 2 pi, which then becomes root 2 over pi. And from that, we can get the area. It's going to be pi. Oh, sorry, there should have been a root there. Pi times root 2 over root pi squared. The root pi squared cancels with the pi, leaving us our answer of 2. So it's a bit messier, but hey, it's an alternative way of doing it. It all checks out. Lots of similar things are happening. I just kind of reverse engineered it here, starting with the radius of the semicircle. And of course, we could have done this whole problem by, instead of writing 1 over root pi, writing it as r instead, and then just finding later on that the large radius was then root 2 times r. That's it. So it's an alternative. I don't know. There's different ways to think about it, but this is my alternative.